Thank you very much. This is the last talk of the day, I know, so I will be trying to be as less painful as possible and also quick. So, my talk is basically divided in two parts. One of it is for about reproducibility, and the next one is for about selection bias. And especially, I would like to focus on talking about the connections between the two. So first of all, what about reproducibility? Reproducibility is one of the most important things in the scientific method and in recent scientific pipelines. So reproducibility can be sort of summarized in two main points. One is to recompute the ability to recompute the results and to replicate. So when I say replicate, I mean getting exactly from experiments the same results. So what about recompute? What are the chances we have? What are the things we should do when we want to be reproducible? Of course, we have tools. GitHub is one of it. So I would say that the very first step is to publish whatever you have on a GitHub repository, so that is publicly available and everybody can get it. If you want to even go further and you want to replicate your environment, which is a nice thing to do, you have some options at different levels. You can replicate the development environment with Conda package, for instance. So you assure that the people that wants to replicate your experiments will try to get into your same environment in terms of libraries and packages, or even further in the same execution environment, which is Docker solution. My opinion, next step is writing documentation. It's very important. And if you want to combine all of these, probably Jupyter is one of the best tools that we have so far, so that you can actually combine and provide in Jupyter notebooks, which is a nice tool to have, examples of how you may run the code and how you may get the results you have. Some people advocate that this is now time to forget about the usual scientific paper in PDF format and having all of this combined together into a tool to replicate the environment and publish the paper as well. So this was for recompute results. How about replicating the same results? So I would say that replicability pillar is mainly founded on random seeds. This is something you don't have to forget about. Once you want to be basically you want to be replicable, you have to set random seeds when you do experimentation. This is very important. I know if you already know it, probably it's silly and stupid for you, but probably my own experience is not that clear to everybody. So I decided to put that very crystal clear into the talk. In NumPy, for instance, you can set a random seed, or if you're using more, let's say, in fashion libraries like TensorFlow, you can also do that in TensorFlow. So you have to set random seed whatever you're doing, and this is paramount, especially because lots of operations in machine learning involve randomization, probably more than you expect, and so setting the random seed, is very important. In fact, you can set the random states even in scikit-learn model. This is the case of random forest classifier, but this is just one of many. So lots of classes in scikit-learn have this parameter, which is random state, and this serves the purpose of setting the random seed. Or this is classical machine learning, but even if you're doing deep learning, this is even more important. This is a few lines of stupid multi-layer perceptronic errors. As you may probably spot from these few lines, I set very crystal clear the initialization parameter. And when I set the initializer for the weight and the bias of these dense layers, basically I set also the random seed I want to use. You can also have different seeds for different layers. It doesn't matter. The important thing is that you fix it, okay? Because the next time you're going to rerun the same code on the same data, you're going to have the same result. That's guaranteed. Otherwise, it's not. Okay? This is one of the most important things to keep in mind when you want to have replicability of your results. Yes? Right. Uh-huh. Yeah. Right. So I repeat the question for the video. So basically, the question is, I can got from your example when you're simple and stupid things, but what about a complex pipeline? I can get scared about how many seeds do I have to fix. Basically, it's important that you fix at least once. You can most of these basically rely on the same seed, especially in case of even in case of scikit-learn. In case of Keras and scikit-learn, they both rely on TensorFlow seed or NumPy seed, respectively, so that if you fix it once, you basically fix that forever for all the pipelines you have. In case and the random seed stands for one execution flow, right? So this is the general case. Of course, it may vary depending on the context, but this is the general answer I feel I can give you. This is considering an execution on a CPU, because on CPU is so far everything is fine once you got the seed. What about the GPU? Well, NVIDIA cuDNN has some documentation saying that there are some operations on cuDNN that may not be deterministic, may not be reproducible. What this means? This means that if you change the environment, if you change the version of the library, if you change the hardware architecture you're using, well, NVIDIA does not guarantee that the results will be reproducible. Okay? So once you're dealing with GPUs, my advice is fix it in an environment. Docker is a good one, and then go with it. Okay? There are some operations very documented. This is from NVIDIA documentation, actually. Especially some of them involving convolutional layers and convolutional operations, that basically saying that if you change the environment, basically they're not guaranteed to be reproducible anymore. Okay, so this was about the computation. What about the connection between reproducibility and machine learning? In other words, what I mean is that reproducibility may be a sort of measure on how confident are the predictions you got from the learning, from the machine learning. And to talk about that, I have to go back a bit and introduce you the selection bias. But before that, I would like to talk about the bias problem. Let me do, please, a quick check. Can I assume that all of you understand when I say supervised learning? Okay. Is there anybody who doesn't know that? Okay, I will introduce you in a quick second. What about cross-validation? Do you know that? Okay, fine. So very quickly, when I say supervised learning, you have a machine learning algorithm and some features coming from input data and the labels. These are the supervision you got. And so you combine them to train an algorithm that is able to generate predictions on new and unseen data or for which you don't have any labels, and so you want to predict them. That's the main purpose of the machine learning algorithm. So predicting labels for unseen data that you've never seen before. So when we build a machine learning model, our main goal is to keep the error we got on the predictions as low as possible. There are two major sources of error when we're building models, and those are called are named bias and variance. If we manage to reduce these two, the bias and the variance, then we're good to go, and we are going to have the best model we can get. Of course, this is the assumption we always have to keep in mind. In machine learning, we usually say garbage in, garbage out. If your data is bad, your model is not going to learn anything. Okay, so we're assuming that the data are good to learn something. So my question now is how we diagnose the bias and variance problem, and what are the action we should take in case we have problems. When we're talking about bias and variance, we're basically dealing with the so-called and so famous problem of generalization. So how general is our model? How general are the predictions generated from the model? And I found this very, very funny, this X case ID about generalization. So in terms of generalization, the usual problem of generalizing something. So when you say, no one has did, in this case it's candidate of the US presidency, no single candidate has won the election without something. And this goes from 1788, goes on and a plenty of them. Okay, so this is the effect of generalization. But what about machine learning? Typically what we do in a usual pipeline in machine learning is that we have all the data, then we split these data in two sets. We have training and test data. This is one line in scikit-learn. We have these functions, train, test, split. We can decide what's the size of the training, and keep in mind that here I'm fixing the seed because I want to be reproducible. So every time I rerun this, I basically get on the same data, I get the same split. And then we use the training data to train the model, and then the test data to generate the prediction and evaluate those predictions using the test labels to see how the model was doing, basically. Okay, so what's the general assumption in machine learning? We have features on the left, targets, and we assume that there are some relation, some function connecting the two, right? There's a general function connecting the data and the predictions and the targets. And typically this function f is almost completely unknown, and so we try to estimate it by defining an f1, f hat, which is the machine learning model that tries to estimate these relationships. We have many options, so we can pass to the same model multiple versions of the data, okay? And so we can have different training sets. And so the amount by which the model varies as we change the training set is called the variance, okay? So we have one fixed model, we change the training sets, and the amount of which these changes, this is called the variance. Another case may be we fix the data, or even we don't, but we change the model, okay? And the assumptions we do when we fix those models basically is called the bias. So the bias means that we're assuming that the relationship has a sort of shape or a sort of nature. And so we are assuming that the relationship we're going to estimate from the data is of that specific family of functions. These are the two examples. So in this case, we have a very high bias learning model. So in this case, we're assuming that in these cases, linear models can learn the connections between data and predictions. And on the other hand, this is a very low bias learning rate because basically we're very, very specific to the training set. In other words, we're very, very overfitting on the data we have. So here we have a very high bias because we're not we're trying to be very general, and the model is very simple considering the prediction at hand. In this case, it's very overfitted. Okay, what we basically know is that the bias variance is actually a trade-off. In the best possible word, we want to have the variance and the bias as low as possible to get the best model, but actually this is not the case. So this is called the bias-variance trade-off. Once you increase the complexity of the model, basically you reduce the bias, but you increase the variance. And on the other hand, once you reduce the complexity of the model, so you're dealing with very simple and stupid models, let's say simple and linear models, well, you increase you reduce the variance, but you increase the bias. That's basically the so-called bias-variance trade-off. And so basically the job of machine learners is trying to fit into the best cases in which you get the trade-off best. This is a very nice example I found on the web. So a comparison of high bias, low variance, and high variance, low bias. So on high bias cases, you have a very niche model that is fitted on a very tiny part of the data you have. And on the other hand, it's on the high variance, you're basically going random picking, but probably you're not going near your actual goal here. Okay, so what we do typically is we extend the concept of splitting data even further. So all of you know that we split the data not only in training and test, but we also save some data for validation. And these introduce what is called the learning curve. So typically, the question now is, what happens to the training error when we increase the size of the training set? Because typically, especially when you're dealing with deep learning, one quite common assumption is that you need lots of data, right? So typically, when you go to a machine learning expert and you say, okay, I want to do this prediction, I have this data, blah, blah, okay. The very first things he or she is going to tell you is that, okay, do you have the data? Well, fine. How many did you have? Because samples are so important for machine learners. And especially on deep learning, a very common case is that you need lots of data to work. And so this is the concept of learning curve, studying how the model is performing, increasing the number of training samples you have. And you evaluate these on the training set, and you keep on comparing the training and the validation error, basically. So you have one learning curve for the training set, one learning curve for the validation set, and in the very end, your goal is to try to understand what's the gap between the training and the validation curve. The gap meaning the difference of the errors between the training error and the validation error. So the smaller the gap, the better the result, of course. There's also irreducible error. That means that basically you cannot reduce to zero these errors. So you always have some errors, and your goal is to reduce these errors as much as possible. In scikit-learn, to show some code, you have this learning curve already available to you, so you can actually use it. Probably you can spot here, there is the CV parameter in the learning curve, meaning that you can integrate this into a cross-validation pipeline. What we do when we do cross-validation, typically the idea is that we have all the data here, the training set, we divide this data into folds, and so one at a time, one fold goes into the validation set, and the others in the training set, and we repeat these for all the folds. So at every run, single run, basically, fold 1 here is in validation, and split 2, fold 2 is in validation set, and we go on, so forth, until all the splits goes until once into the validation set. We have many options for that. We can do classical k-fold. So k-fold means that you specify how many folds you want, and so the data are splitted into folds of the same size in that number. So meaning, in this case, we have 5 folds. So in blue, you see the training data. In red, you see, the validation data. And so you see that the folds goes to the validation set one at a time. If you increase the number of folds, of course, you have more splits. You also have another option, the shuffle split. So you can generate the data into the validation sets by picking randomly data going into different folds. And of course, these increases the number of iterations. So the greater the number of iterations you have, the better the generalizability you have. And also another option is this well-known stratified k-fold. The stratified k-fold means that you want to guarantee, this is very important. Sorry, I'm playing with it. It's pain in the ass. So, the stratified k-fold means that you want to guarantee that samples belonging to, in case of a classification problem, belonging to the same classes stands in the training and validation folds in equal proportions. So you imagine that you have two classes, okay, very unbalanced. So you have 100 samples of one class and 50 samples of the other class, and you split in two. So basically the proportion of the samples between the two classes stands equally in the training and validation steps, in validation splits. Okay, so this is stratified k-fold, the stratification. Okay, if you want to apply cross-validation in a replicable way, one option, of course, is to fix the random seed every time. So again, if you want to make it replicable, fix the random seed. So this is for general bias. What about the selection bias? Okay, selection bias meaning is that it's the bias that happens when you select the data in such a way that proper randomization is not achieved. The sample obtained is not, typically this is also called selective bias, and this happens on the sample size, meaning that you selected a set of samples in your training set, which is not very representative for the general case. And so you have no chances that the model is going to generalize in that case. If the selection bias is not considered, the conclusion you may derive may not be accurate. And so one option is to push even further the idea of the cross-validation by doing what is called the nested cross-validation. So when you want to do nested cross-validation, typically is that you want to replicate a fixed number of times, let's say CVN in this case. You want to replicate a stratified k-fold in this case. So we do cross-validation a n number of times, right? Something I want to point out from this is that, again, I fixed the seed here, and in this particular case, the seed corresponds to the iteration step. This is one option, of course. You may decide to fix as many seeds as you want, but in this case, this allows to have a pipeline which is replicable. In this case, we are fixing different seeds so that, this is very important. I hope you get it, because if we don't fix it, okay, on one hand, we are not guaranteed to be reproducible, because we're not getting the same results, and fixing different seeds guarantees you that the generated splits will be different at the different iteration steps. Okay? Yes. The nested cross-validation, actually, is has suggested by the Bible of machine learning, elements of statistical learning, is typically to be used, a typical example to be used of tool you have in your weapons in different configuration. Typically, you do a 5x3 cross-validation for hyperparameter search. So in this case, your focus is to look for the different hyperparameters. And so in this case, you have sort of combinations of hyperparameter, and you're splitting the data to find the best hyperparameter for your data. And typically, a 5x3 cross-validation is fine. When you want to tackle with selection bias, and so the problem is how stable are the models you're going to produce and the predictions you're going to use by the models. And typically one classical configuration is 10 times 5 cross-validation. This is the case, the second one, this is the case we're going to deal with in the next slides. So if you want to write down a to-do list for the nested cross-validation, typically these are the things you have to do. You have to initialize and set random seeds, that's paramount. then you have to be sure that you create, this is important, new models at each run, because you don't have to overfit and overfit again the same model. Every time you run learning on a different split of data, the learning model has to be new. Okay? Otherwise, yes. No, the seed is the same, but the model should be reinitialized, meaning the hyperparameter should get the default values. Yes. You get it? Because you don't have to basically refit. Because if you're changing the data splits and you're fitting the pre-trained model on different splits, you're basically retraining the model on the same data. And so you're getting no clues on how good are these predictions. All right. So the model should be new every time. Random initialization is set up front. Yeah. You have to calculate the error or the metric you have at each run, and important, you have to average them and get the confidence interval. This is paramount. In case you're going to have a 10 times 5 cross-validation, you're going to have 50 different splits of your data. Okay, so calculating the average and the confidence interval is very, very important, because the confidence interval, especially having some bootstrapping in this confidence interval, is very important, because you get basically how stable is your model. If you get on, because you can get the best result you may have on one split and the worst result you may have on another split. Okay, and this is the principle of randomizing all of this. Otherwise, you may end up with a model that works very good or very bad, depending on the splits you prepared on the data. But this is not stable at all, and you cannot rely on such a model, especially in cases in which predictions should be trustable. We're hearing a lot of people talking about reliable machine learning, interpretability, and the general case in which I typically deal with in my job is having to process medical data. And when you have to deal with this kind of data and you want to rely on the predictions, you have to be sure that the model is not underfitted or overfitted, but you can really trust on the predictions, especially when we're talking about the patients and the health of people, right, of patients. And so you have to be sure that your prediction may be reliable in some way. Okay, you have to trust on them. And finally, you have to save your models and checkpoints, because you want to be replicable. So all of this is a lot of boilerplate. And so these, if you think of it, I didn't specify any specific machine learning or deep learning model. It's totally model independent. It can be easily tunable to be used with machine learning and deep learning. Actually, the difference in deep learning is that you have to reinitialize the weights of the network. And in the case of neural networks, you're going to have lots of more hyperparameter rather than typical in classical machine learning, but the principle stands. And what about additional things you may plug into this pipeline? Feature normalization, for instance, or feature selection. When you're dealing with, when you're dealing with biological data, which is the case I typically do, you're going to have a very high dimensional sets of features. The data sets we use to work with are typically large in feature-wise, but not that large on sample size. So you have few patients and thousands of features that you may use, but none of them, or all of them, or some of them may be reliable for the prediction. So feature selection is another thing you may want to plug in into this selection process. And what happens if you change the features on specific splits of the data? So this is the case of this package I built. This is called Reproducible Learn. Actually, it had a different name, but you're going to discover it in a second. This is available on GitHub. And this is so, at a glance, what it does, it's pure Python based. It's a sort of high-level framework that tries to be framework agnostic. Actually, it's not yet. It's one of the features in the to-do list. And this is mainly based on what we call the data analysis plan or protocol, DAP. I'm going to tell you in a bit. Some details on the software engineering part of this. This is based on some specific settings. These settings are specified in a single file. So it's actually settings. Where is it? Settings.py. So it's a Python base where you can set the settings just like you do in Django. And you also have a specialization of this for deep learning. So you have additional settings in case you're dealing with neural networks. What about the DAP, which is the core processing of this library? It works this way. So it applies a nested cross-validation, actually. You have the training set here and test set that will go on the final prediction and evaluation. So this is a nested cross-validation, but it's a little bit more complicated than usual nested cross-validation. You have your internal training, you have your model you want to test. In this case, we're talking about biomarkers because that was used for biological data, but this stands for every data you have. So here in this step, before you're doing the fitting or the training of this model, basically you may normalize the feature. Then you can also select the features. You can apply feature selection. And in the feature selection, meaning that you may say, okay, I want these number of features. Let's say I have, real case, I have 45,000 features. I want to select the 5% of them, the 10%, the 25, or the 75, or all of them. How the prediction changes if I select these features. How can I select these features? Basically, there are algorithms that may rank the importance of the features. So you can rank the features you have and select the portion of those features you want, run the model, you do the prediction, and basically you get the evaluation on the internal validation step. This step is achieved, of course, in the cross-validation. And so every time you have a run, you have a ranking of features, and in the very end, you have the best features for your model, and this comes from the best ranking you may get, or an algorithm which is called the board algorithm, which is an algorithm to evaluate the different rankings. And so you have many, many rankings, and you get the best features, so the number of features that best predicts on the data you have, and the selected features are those appearing in the highest positions in the different rankings. This is one option. This is called the board algorithm. I will tell you details later on. So the last step is this one, and this is important. Once you got the best model, okay, the best model is retrained on the entire set of data, because this is what you do when you do cross-validation. Once you got the best configuration and the best selection of features, you rerun the training of the model, and then you test it on the unseen data, selecting the features that results from these complex pipeline. How this is implemented, this is just one class. It's an ABC class in Python. It's pure Python 3. It has some support. So far it's a little bit experimental, but we're working on it. It has some support for parallel processing, because as you probably imagine, once you run every single iteration step, every single iteration is embarrassingly parallel. They are totally independent. And so you can run them on multi-cores or multi-GPUs if you have. And the main class, which is the DAP, is an ABC class that implements what is called the template method. So the main algorithm is implemented in this class. What is missing are just the steps. You will going to fill in by extending this class. It's quite well documented, so if you take a look at the code, it should be straightforward. And also this ships with runners. So in case you have very classical cases of random forest, SVM, KNN, or even simple and stupid deep neural networks, they are already built in for you. So you just have to feed the data into this and call the run method, and it works. So improvements here and to-do list for the future. Of course, we have to improve the parallelization. It's so experimental right now. We have to integrate DB analytics. So far, it's very, very flat file based. So it's the metrics are and all the generated data are saved on flat files. So far, scikit-learn and Keras models are supported. I had in mind to do a framework agnostic tool so that you can have a very general and high-level thing. You can plug in PyTorch, you can plug in whatever you want. The only difference is in the method you have to call to run the training of the model. That's the only difference. And integrate multiple metrics. So far we have a series of metrics for regression and classification, but this is still plugged in into the code, so could be improved, of course. Okay, that's all I have. Just a very quick reminder: we have this contest available in PyData. It's available in contest.pycon.it. You can sort of reuse some of this, maybe as a hint. And that's it. Thank you very much.
Okay. Thank you, Valerio. Is any question? Okay.
Hi, very interesting. I never used nested cross-validation. In cross-validation, you have, for each combination of parameters, you have a single score, while using nested cross-validation, as far as I understand, you have multiple score for each combination,
yep,
so that you can build multiple a confidence interval for each combination.
Mm-hmm.
And in the end, how do you choose which one or which combination? Do you use, for example, some hypothesis testing in order to choose the best combination of parameters?
Yep. No. So yeah, that's true. So in the very end, the selection, in my case, typically happens on a feature-wise case. So I basically have 10 times 5 CV and different feature steps. I call it feature steps, so different portions of the features. And then I select the best, so the highest or the lowest, depending on the problem metric, according to different feature steps. Looking at the average value and the confidence interval.
Okay, thanks.
Question?
Just clarification, actually, the best is automatically selected by the framework. So once you got the best value, these are going to be the feature, the final feature, number of features you want to use. And so you rank the features according to different ranks you got into the, let's say, 200 runs. And so you rerun everything on the entire training set and you do the prediction.
Yeah, so I had a question to your initial mentioning of CUDA and like reproducibility on the graphic card. So my question was, did I get it correctly? You mentioned if you change the context, it might happen that it's not, the calculation might be different. So does this include the hardware? Because this is something that...
Yeah,
so
I can actually re-show you the slides. It was stated very clearly into the, sorry for that, I cannot find it. Where is it? Or, oh my goodness, oh yeah, sorry. Yeah. All CUDA routines from a given version generate the same bitwise result across runs, however, blah, 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 with the same architecture and the same number of SMs with us.
So meaning if I pack my whole project with all the data into a container or something, but then someone executes it on a newer generation or something, it might get different results.
Yeah, yeah. Okay. I can tell you by my own experience, if you change, for instance, the version of the cuDNN, even on the same CUDA library, results change. And so this is why typically when you do GPU computation on deep learning stuff, it's a very good idea to specify what was the hardware you use. What was the architecture? Not the specific hardware. The architecture is very important. So let's say Maxwell, Pascal, or Volta, whatever you want.
Any other questions? No one? Okay. Thank you, Valerio.
Oh, probably one.
Yep.
No problem. No, it was not sure.
Fake applause.
Sorry.
I was wondering, just really a rough approximation of, you have to loop many times to retrain and test inside these different cross validations. What's the average size of data set or number of iterations or size of model which you can run on your laptop feasibly? Just a rule of thumb.
Yeah, in case of the classical machine learning, let's say SVM or random forest, it works on a laptop in a bunch of seconds. But it really depends, especially when you have very high number of samples. SVM is not that good. SVM is not supposed to be run on very big data sets. Random forest is super fast. Deep networks, of course, it's a bit huge. And the execution typically is best to run on GPU, especially because you want to do more complicated things. So laptop is not well suited.